Okay, this is going to be more from section 8.7. We're still talking about Taylor polynomials, and in the last video I showed you just the steps on how to find them. Not much of the behind the scenes, but just getting those steps down, and we're going to do something similar today. I'm going to show you what's called the remainder of the Taylor polynomial. It's named after somebody named Lagrange or Lagrange. I'm sure it's probably pronounced. This one, the formula looks crazy. It seems very complicated, but we're going to try to break it down and get it nice and simple. So let's start by finding a Taylor polynomial. Actually, this one's going to be a Maclaurin. Maclaurin, if you remember, is a Taylor polynomial centered at 0. It just has a special name. And the function is going to be the natural log of 1 plus x, and we're going to find the fourth degree. So if you remember the steps, we start by taking all the derivatives. So you might think with this natural log function, those derivatives will be real difficult, but it's not bad. The derivative of the natural log of something is 1 over that something. So I'm just going to write it like 1 plus x to the negative 1. And then this pattern of derivatives seems pretty simple. Negative 1 times 1 plus x to the negative 2. The chain rule doesn't apply because the derivative of 1 plus x is just 1, which makes this a little bit easier on us. Then we get 2 times 1 plus x to the negative third. And finally, our fourth derivative is negative 6 times 1 plus x to the negative fourth. And I want you to, before that, first let's go in and plug in. Plug in 0, because this is Maclaurin. If we were centered somewhere else, that's the number we would be plugging in. So my first one is the natural log of 1, which is 0. My next one is 1 over 1, which is 1. And then I get negative 1, 2, and negative 6, which are just those coefficients because the 1 to whatever power stays 1. Now, to write our polynomial, if you recall, we do derivative for each term over factorial and then power. All right, that's just a very informal little memory trick, derivative, factorial, power. So what that means officially is I'm going to take my my 0 degree. I'm going to list out the degrees of the terms that I'm dealing with. I'm going to start with 0, and that's just my function itself. So I'm going to put all the terms. A lot of it's going to go away, but I'm going to write them anyway. My my 0 derivative, which is just my function, is 0 factorial. And this, because it's a Maclaurin, is just x. It's not x minus some center. That's to 0. All parts of that, well, 0 factorial is 1, x to the 0 is 1, but that 0 wipes that term out. So that term is not going to show up at all in my final answer. Okay, my derivative from the chart that I just made is 1 for the first degree, 1 factorial, and then x to the first. All right, not x minus anything. Remember, this is our center. It would be x minus 2 if we were centered at 2. Okay, so next, my derivative is negative 1, my factorial is 2, my power is 2. The third degree term, my derivative is 2, my factorial is 3, my power is 3. And then negative 6, 4 factorial, x to the fourth. Okay, so let's clean that up and make it a nice, neat polynomial. We could write it p sub 4 of x, meaning the fourth degree Taylor polynomial. The first term's completely gone. The second term is just x. I guess you could call that the first term. The 0 term is gone. The second term in my overall answer is 1/2 x squared. You could write it as x squared over 2, but I like to kind of keep it separate to emphasize what we're doing here with the 3 parts. The next term is going to be a third x cubed. All right, it looks like it might be 2/3, but remember 3 factorial is 3, 2, 1, and the 2's will cancel. And then in the next one, I've got 4, 3, 2, 1 on the bottom. The 3 and the 2 cancel, leaving just a 4. So this is the fourth degree Taylor polynomial for natural log of 1 plus x, Maclaurin polynomial. So it's Taylor centered at 0. I wanted to show you just real quickly on the calculator. I'm going to graph it a term at a time. Here is the function we're dealing with, natural log of 1 plus x, and then the first degree, which would just be y equals x. Okay, so the first term here, y equals x, that should be a good approximation of this function near 0. So if you look at this graph, you know, from about here to about here, I can't even really tell the difference. And part of that is weak graphics, not zoomed in too far. But part of that is that straight line is a pretty good indicator of that function on that small little window. So let's add the next term. There's the x. My next term was minus x squared over 2 and when I graph that, I should get a parabola that's pretty close. Now, if you look at the parabola, it's indistinguishable from about here to about here. So I got a little bit better by using a squared function than I did a linear function, but it's not great. I'm going to skip the next one and go right to the fourth degree. X minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. Confirm and make sure that was right. Plus x cubed over 3 minus x to the fourth over 4. So here's my fourth degree Taylor polynomial, and let's keep that those same red and blue marks and look at this graph. So this is the best case scenario. This function is fourth degree. So you can see it joins in here, you know, and we get wider a little bit each time. So as our degree goes up, our resemblance of the actual function gets better and better. That's what a Taylor or Maclaurin polynomial does. Okay. Next, the whole purpose of these polynomials is to estimate the value of a function. Okay, so for instance, I could use this polynomial to estimate the natural log of 1.1. Okay, that's the point. When you didn't have a graphing calculator in computers, and this is actually how your calculator will work, it will use an infinite series or a bunch of terms in a series to add up natural log of 1.1. When you type natural log of 1.1 in your calculator, it doesn't have them all memorized. It doesn't have a giant chart full of natural logs programmed into it. It uses something like this Taylor polynomial. So natural log of 1.1 should be pretty close to 1.1 minus a half of 1.1 squared plus a third of 1.1 cubed minus a fourth of 1.1 to the fourth. And we know that's true because natural log of x plus 1, excuse me, let me make a slight adjustment there. What I meant to say was 0.1, 0.1, because my function was natural log of x plus 1. So if I want to estimate the natural log of 1.1 using this polynomial, which is approximately equal to the natural log of x plus 1 or 1 plus x, I need to actually plug in 0.1, not 1.1. Okay, so now I'm going to pause and type this in my calculator and see what I get. Okay, so I'm back, and you can just write down these values. If I plug 0.1 into my polynomial that we just formed, I get 0.095308. If I actually take the natural log of 1.1, which in my calculator I can assume is accurate out to as many places as my calculator will show, these are pretty close. Out to the 5th place, and if I rounded it, even the 6th place, it looks like would be accurate. So here's the big question of the day. How close is any polynomial that we use? How close to the actual value is it? You're going to see some similarities between this and our alternating series stuff. Let's start with the formula. Here is the formula straight out of your book. R sub n of x, which is the remainder from an nth degree Taylor polynomial, equals f n plus 1, which is the n plus first derivative, evaluated at some number that we're going to call z for just a minute, over n plus 1 factorial times x minus c to the n plus 1. Now, I know this looks pretty ridiculous, but this means only this much. Take the next term. Once we figure out what this z is, the size of the next term is it's as big as our error can be. You know how in an alternating series we said the sum of the first 9 terms is within the 10th term of the true sum? That's exactly what's going on right here. Let's take the next term in our polynomial, which would be plus 1/5 x to the 5th. There's our next term. If I were to take the 5th derivative and put it over the 5th factorial and do x to the 5th power, that's my next term. That's what would have been right here, right? Now, let's see what this thing means. In your book, if you look at it, it says z is the maximum value. The n plus first derivative at z is the maximum value between x and c. Now, what that means is this z value between x and c that makes this error the biggest. So what does that mean? X and c, those can be kind of confusing. X is the number that we're plugging in. For us, that's 0.1. C is the center, and for any Maclaurin, that is 0. So let's put this all together. Our next derivative would have been 24 times 1 plus x to the negative 5th. Our next factorial would have been 5 factorial. And our next power would have been x minus c. I'm just going to leave it as c for just a second, to the 5th power. So this is the Lagrange form of the error. All right, it's the next derivative, it is the next factorial, and is the next power. Now this z thing, z is the number between x and c, and it's almost always either x or c that makes this the biggest. So let's plug in. If we have 1 plus x to the negative 5th, what's going to make that value bigger? 1 to the negative 5th or 1.1 to the negative 5th? Well, if we plug in 0, because this is actually, a negative power, it's on the bottom, which means bigger numbers make it smaller. So we need to make it as big as possible. So we're going to choose 0. So my error, and all this is in absolute values, I forgot to say, no big deal, is going to be when I plug in 0, I do 24 times 1 to the negative 5th over 5 factorial. X and c are 0.1 and 0, so that's going to be 0.1 to the 5th. All right, so let's put that in our calculator and see what we get. I'm going to pause, type that in, so I can cut this video a little shorter. Okay, so here's our results. The lower number here, this is the number that we got for our error. That was just 24 divided by 5 factorial times 0.1 to the 5th. Okay, and if you look at that term we just created, that's all we really had left. 24. This is basically nothing. 1 to the anything is 1. So 24 over 5 factorial times 0.1 to the 5th. That tells us that the worst case scenario, if we use this polynomial to estimate the value of natural log of 1.1, we are within 2 times 10 to the negative 6th. So what I also calculated on this screen was our error. This number is our error. All right, here's the actual log of 1.1. Here's the polynomial with 0.1 plugged into it, and those were off by 1.8 times 10 to the negative 6th. So what this Lagrange error tells us is we will be within 2 times 10 to the negative 6th of the actual value. And how close are we? We are 1.84 times 10 to the negative 6th from the actual value. So it shows that it worked. We were within the error that it said. All right, so I know that this was maybe not the best video topic, and we will talk about it in class as long as you want to, but just get the steps. Take the next derivative, the next factorial, the next power, choose either x or c, whichever one makes it biggest, because we have to be safe, and that's how you do your error. All right, so I'll see you in class. The 5th great nephew of Brooke Taylor out.